Great to see you here again. Like I already announced in the previous video, in this new video we'll be looking at the RSA Cryptosystem. Now, we know that the crypto systems are basically developed to hide secrets, and states and military have a lot of secrets to keep. Basically, a lot of research is done for the military and for the government, and later those methods are being shared with the world. Now, basically, when we look at the RSA system, it was developed by three people, and that's where the name comes from. It's Rivest Ronald, who gives the R, Shamir Aldi, who gives the S, and Alderman Leonard is in fact the A. It was already known as a system in the 1970s, but it was only put into public use from the 1990s. So for about 20 years, it was used only by governments and military. Now, the encryption system is based on the private key, which is given by a number n and e. There are two elements. There is the modulus n, which is in fact the product of two large primes. P and Q are two primes, and basically we find an let's say a modulus which is the product of typically 200-digit long primes, and it means that we have in fact a 400-digit modulus. So it makes it very secure, certainly because the factorizing with prime numbers is NP. It's not a polynomial. It means there is no polynomial time to find that, let's say, to find those two prime numbers, and it makes the system, of course, very secure. One of the things I have to add here, that more and more systems are being developed, and based on that, more and more larger primes have to be used to keep the system secure. Now, if we could find a polynomial time to factorize integers into primes, that would, of course, make everything obsolete. The second element, the exponent e, is relatively prime to p minus 1 multiplied with q minus 1. So we have to find that element. And in fact, the thing we have to do here is to get those prime numbers with 400 digits. And that's why in one of the previous videos we were looking at pseudo primes and ways to find prime numbers, because the computer will find those prime numbers using another procedure or algorithm. Now, once we have those primes and we have those elements, we will start with the encryption. And let's first have a look how the encryption in principle works. So what we're going to do is to transform a plain text message, I call it capital M, into sequences of integers. And each letter is transformed into a two-digit integer. For example, A is 00, B is 01, up to Z is 25. Now, basically, I already said it before, we can use these counting the starting from A till Z from 00 to 25, or we can use the ASCII codes. If you're looking at some other elements on the internet, you will find that some of those use the ASCII codes, and basically that's the best way to do it, because every letter, every symbol on the keyboard has a specific integer ASCII code. Now, the elements is in fact, what we have to do is that we have to concatenate those two-digit numbers into strings of digits. So we make a string of digits representing the text, the letters of the text that we are using. And then we divide the concatenated string in equal blocks of 2n digits. And we find 2n the largest even number such that the number 25 up to 25 with 2n digits does not exceed n. For example, when we have 2700, then we have 25. The next series of 25 is 3 times 25. So basically, in that case, we're going to use n, which is 2, so we have 4 digits. In our example, we will use with 4 digits, but we also can have larger numbers. We will see when we have those large prime numbers, the even number, the blocks that we will be encrypting will be larger also. Now, we translated that plaintext message into a sequence of k integers. We have a multiple of 2n, so we find m1, m2, and k, and we will now encrypt each block into a cipher text block. So I call the encrypted text block C index I, and we are going to encrypt each block M index I into C index I. And I just write it here in general. Capital C is M to the power E, capital M to the power E, modulus N. And here we're going to replace capital C with CI and M with capital M with M index I. And that's what we're going to do in some exercise later on. So let's have a look at an exercise. It was very late. We have it on the next video, on the next slide. What we're going to do is to encrypt the message freedom using the RSA Cryptosystem with a key, and the key NE is given by 2419 and 11. And 2419 is in fact the product of two prime numbers, which are 41 and 59. So the next thing is to identify the fact that we have to find an E, the E, which we selected, and we have to see that the greatest common divisor of E with P minus 1 multiplied with Q minus 1 is equal to 1. So basically, there is no common divisor larger than 1 between those two numbers. So we have to see 11, okay, we have that E, and P minus 1 times Q minus 1 is 40 times 58, and we can prove that there is only the number 1 as a greatest common divisor between 11 and 2320. Now what we find is the first step is to replace the digits by the numbers. So we have freedom, and we replace each number by a digit. So we have for F is 05, R is 17, E is 04, we have it twice, D is 03, O is 14, and M is 12. We select 4 groups of digits. Between N is between 2525 and then the is smaller than 252, 525. So it means that we use the 4 digits. 2n is equal to 4. And what we do here is we group the numbers as 4 digits. So we have 05 and 17 together, 0404, 0314, and then we have 1 digit left, so we have 12. In order to resolve this, I add x, and x has in fact the value of 23. So basically here I have 4 blocks that I have to encrypt. Let's do that. Let's look at the encryption, and we find the encryption is C is equal m to the power 11 modulus 2419, and we use the fast modular multiplication. I found some calculator on the website decode.fr. You can find it there. You can also write it yourself, or you can in fact do the calculations, but it will take you some time. Of course, you can use those calculators to find the numbers. The first one we have 0517 to the power 11 modulus 2419 gives us 1952. So we do that for all the 4 blocks, so 0404 or 404 to the power 11 modulus 2419 gives us 2227. For 314 we find 1028, and finally for 1223 we find 1085. And this is in fact the result of the encrypted message. We send 4 blocks, which are 1952, 2227, 1028, and 1085. So now we have the message encrypted. The next thing we have to do is, in fact, to find a decryption key. When the receiver has it, the receiver can find the plaintext message by decrypting it using the secret key. But first we have to see what is the principle of the decryption in this case. So let's have a look. The decryption, we transform the coded message back into a plaintext message, and now we start from a series of integers grouped in series of 2n, and we have to find the original block of integers. Now we can use it as integers, as letters, or as integers. It doesn't matter, it's just going through the system anyway. When we use the integers, we don't have to transform the letters again into numbers. Now let's have a look. The decryption is easy because we know the decryption key, and the decryption key is an inverse of E modulo P minus 1 times Q minus 1. Now, of course, decryption is easy once we know this key. Now, how do we find this key? We know that basically the inverse exists because the GCD of E and P minus 1 times Q minus 1 is equal to 1. So once we have this condition, we know that there is an inverse, and we will call that inverse key D. What we say that the inverse multiplied with E, the inverse of E multiplied with E, is congruent with 1 modulus P minus 1 Q minus 1. And once we know that, there is an integer k for which we can write that D times E is 1 plus key times P minus 1 times Q minus 1. And basically this leads to the expression that C to the power D is congruent with ME to the power D, which we can say is M to the power DE, and we can replace the expression of DE in this expression. Now we can say that M is equal to the power 1 plus k times P minus 1 Q minus 1, and this is an important element that we have here. Also, when we want to create the inverse, we can use the property of the modulus, and we can say that the DE minus 1 can be divided by P minus 1 times Q minus 1, or P minus 1 times Q minus 1 divides DE minus 1. So basically that's what we're doing here. Now, when we look at the formulas, we know from Fermat's little theorem that the greatest common divisor of M and P is equal to the greatest common divisor of N and Q. So that's a very important property that we have to consider. And we can say that NP minus 1 is congruent with 1 modulus P, and MQ minus 1 is congruent with 1 modulus Q. Based on this, we can say that C to the power D is congruent with M times MP minus 1 to the power K times Q minus 1. And we know that this part, M to the power P minus 1, gives us 1. So we can say that C to the power D is congruent with M modulus P. On the other hand, we can also say that C to the power D is congruent with M modulus Q. And when we multiply, we find that C to the power D is congruent with M modulus P times Q. So basically that's the formula we're going to use to decipher the RSA encrypted message. Let's now apply it on an exercise. So we are using the same encrypted message we found before. So we have 1952, 2227, 1028, and 1085. Now we encrypted this message using the key N is 2419 and E is 11. So first of all, we have to find an inverse of 11 modulus 40 times 58 is equal to 2320. Now we have to find, in fact, the inverse, and we've already proven by the selection of N and E that an inverse exists. Now we can say that 11 times D is equal to 1 modulus 2300, or congruent with 1 modulus 2320. So we can say that 2320 divides 11 times D minus 1. And when we try to find it in Excel or in another way, we find that D, the inverse, is 211. When we look at the decryption formula, we find now that we can find the plaintext capital M, which is equal to capital C to the power 211 modulus 2419. The thing what we can do now is to resolve this for the different blocks. So we find C1 is 1952, C2 is 2227, C3 is 1028, and C4 is 1085. So those are the encrypted blocks that we found before. We put that now in the different equations. We can use the fast exponentiation, which is described on the side, or you can use a program that you made yourself. You find that for M1, it's 1952 to the power 211 modulus 2419. So I find 0517. For M2, I find, when I apply the element again, is 0404. For M3, I find 03 and 14. And for M4, I find 12 and 23. So basically what we have, we find the different numbers that we can link to a character, which is 05, 17, 04, 04, 03, 14 and 12. I took out the 23 because we added the 23 to have 4 blocks, and we know that the letter corresponding with 23 is X. So we know that we find freedom X. We know that the final result is basically freedom because the X has no sense here. So basically these are the calculations, and this is how we encrypt and decrypt messages using the RSA method. Now, the next session will be about cryptographic protocols. We're going to see how we can use these elements to share keys over a public network, or how to identify that a message originated with the sender, let's say with the correct sender, so we can verify to see that the person who sent the message, who claims to be a certain person, is really that person. Encryption is very important. It's not so easy to do. You have all that modular arithmetic, but it's very important to understand it. Anyway, you're doing a great job, and I hope you enjoy it. It's a little bit more mathematical, and people who like math typically like these things. So basically, we will continue in the next video. This is the end of this video, and I'm looking forward to seeing you there. Thank you, and bye-bye.